Hello grade 12s, this is an explanation of question 6, which is the acid and base question in the prelim. So consider the following 3 inorganic acids in the table below, all of which are classified as weak acids. So nitrous acid, sulfurous acid, hydrocyanic acid. They've given you the formula and they've given you the Ka values. Now remember, the Ka value shows how much something ionizes in water. Now you can see these are weak acids because they've got to the minus something. So it's 0,00072. So they're not ionizing very much in aqueous solution. So it makes them weak acids. But of these weak acids, they don't all have the same strength. So one may be stronger than the other. And so the Ka value, because all the Ka values are different, it shows different ionization in water. So this one, the sulfurous acid, is only times 10 to the minus 2. So that one is a bigger Ka value than nitrous acid. And then the HCN has a very small Ka value. So remember, the strength of an acid is shown by how much it ionizes in solution. And so that means the one with a higher Ka value will ionize more and will be the stronger of the weak acids here. So it says, define a weak acid. So we get that from the SAGS document. Identify the acid in the table that is diprotic. Remember, diprotic means that it's got 2 H pluses that it can donate. And so the only one that has 2 is H2SO3. Rank the acids in the table from strongest to weakest. So the strongest of the weak acids will be the one with a higher Ka value because it indicates that it ionizes more than the others. And so goes from the highest Ka value to the lowest Ka value. Then, so from strongest to weakest. Then give a reason for your answer. So you can't just, most of you lost a mark here because you said the higher the Ka value, the stronger the acid, but you have to say why. You have to include why, and it's because it ionizes. And it's the strength of the acid is linked to the ionization. So you had to say the higher the Ka value for an acid, the more it ionizes in the aqueous solution, and therefore the stronger it is. So don't leave out that ionizes part. Then under controlled conditions, sulfurous acid can undergo neutralization with potassium hydroxide in 2 steps, and there are the 2 steps. KOH is a strong base. Circle the correct words between the brackets in the following sentence. So if it's a strong base, we know that KOH, it's a metal, and we've got OH, the hydroxide polyatomic ion. So it's a metal with these non-metals, so it's ionically bonded. And so if it's ionically bonded, it's got ions already. So when it reacts with water, it just has to dissociate. And so it will dissociate because it's ions already, and it will be completely. So we take it, strong acids and strong bases either ionize or dissociate completely in water. Then an amphiprotic substance is a substance that can act as either an acid or a base. And then they've given us HSO3 minus, and they've asked us to show it reacting as a base. And so if it's reacting as a base, it means that it must receive an H plus. And so if it receives an H plus, that H plus is basically cancelling out that negative over there. And it will be H2SO3. And then because the H2O has lost an H plus, then it's more negative. So it's the OH minus that is left. Then identify the conjugate acid-base pairs in reaction 2. So here was the step 2 of the reaction. And so remember, acid-base pairs only differ by an H plus. So we know this one is the acid, and its base partner is this one. They only differ by an H plus. And then over here, we've got the OH minus, and the OH minus in this step receives an H plus to make H2O. It differs only by an H plus, and so this OH minus would have been receiving an H plus. So this is the base, and then the water over here would be the acid, the conjugate acid. Then, during the complete neutralization of sulfurous acid with potassium hydroxide, a salt, potassium sulfite, is formed. So remember, the sulfurous acid is a weak acid, potassium hydroxide is a strong base. So the salt that is formed, this K2SO3, remember salt is an ionic substance, so it's made of positive ions and negative ions. So it will be K plus ions and SO3 2 minus ions. Now we know that the K plus comes from a strong KOH. So the K plus is weak and it will not react further with water. We've got SO3 2 minus. It comes from the weak acid. So this ion is strong, and so that ion will react further with water. Remember, in an acid-base reaction, you use a single arrow, but in the hydrolysis, you use the double arrows. So, as we've already said, it's asking, let's read the question, state whether potassium sulfite is an acidic, basic, or neutral salt. Even in your head, you must say, weak acid, strong base, base is winning, so we know it's going to be a basic salt. But you have to be able to scientifically explain that. The hack is so that you can just know what you're heading for. So we know that it has to be a basic salt. And they're asking then, would an indicator, methyl orange, that changes pH 4.4 be suitable? Now already with our hack, we know that the salt is going to be basic, so that would not be suitable because that's changing that would be suitable for an acidic salt. So, as I said, the K plus ions will not react further. The SO3 2 minus ions will react further with water. Remember, you're using ions here. You can't just put SO3 or a K. You have to have the ions. Now, when we show the SO3 2 minus reacting with water, we use the double arrows, and then it always is going to form what it came from. So we know that SO3 2 minus comes from sulfurous acid, so it's going to form sulfurous acid. And because it receives H's from the water, we're left with OH minus. And so our OH minus ion concentration has increased, therefore it's a basic salt, therefore the pH of the salt solution is greater than 7, and so that's where the color change will happen. And so it would not be a suitable indicator because this one, the pH is around 4.4, and we need one that will change greater than 7. So phenolphthalein would be a good indicator. Then, in the titration, 25 centimeters cubed of sulfurous acid, that's got the unknown concentration, so we're going to use the whole titration to find an unknown concentration of the sulfurous acid, was titrated with the standard KOH solution. Remember, standard solution, we know the concentration of that solution. Then they told us they don't give us the concentration of the solution. They have given us the information that they used to make the standard solution. So the mass of the KOH was 2.8 grams, and they dissolved it in 200 centimeters cubed of water. But they didn't use the whole 200 centimeters cubed of solution that they made. They only used 33.6 to get to the color change. And that is what we use in the stoichiometry to calculate the unknown concentration. So, standard solution, solution of known concentration. Explain the difference between the endpoint and the equivalence point. The endpoint is where the indicator changes color, and the equivalence point is where the acid and the base have fully reacted, where neither is in excess. Now, they've just asked you to calculate the concentration of the standard solution. So we've got the mass of the KOH, so we say number of moles is mass divided by molar mass, and there's a potassium, an oxygen, and a hydrogen, so the molar mass is 56. So we're using 0.05 moles of the KOH. We dissolved it in 200 centimeters cubed. Here we divided by 1,000 because we need it to be decimeters cubed. And so the unknown concentration is 0.25 mole per decimeter cubed. Well, unknown in the sense that we had to work it out. So this is the concentration of our standard solution. So now you've got a bottle of 200 centimeters cubed of the KOH with this concentration, but you don't use it all in the titration. And I know I'm harping on about that, but many people just use the 200 centimeters cubed and not the 33.6. So now, to determine the unknown concentration, so step one in our stoichiometry, let me just move this across, I can't, okay. Step one in the stoichiometry is you work out the number of moles of the standard solution. So because we are working out the number of moles used, we didn't use the whole bottle. So we know the concentration is 0.25. We know we use 33.6 centimeters cubed, so we're dividing it by 1,000 to make it decimeters cubed. So we only used 0.0084 mole of the KOH solution. Then we look at the ratio. So we look at the ratio, so KOH is 1 mole, and we need to find the unknown number of moles of H2SO3, so we're using the ratio. So we've got 0.0084 moles of KOH. The ratio is 1. Oh, I think that must be a 2. This must be a 2. Please hold. Let me just go and check our balanced equation. Yes, that must be a 2. That must be a 2 there. Okay, so it's worked out correctly though. So you can see the ratio is 2 to 1. So if you've got 0.084 moles of KOH, we times by 1, divide by 2. You're only going to use 0.0042 moles of the sulfurous acid. So that's what we're trying to get, the number of moles of our solution that we don't know the concentration. Then step 3, we calculate the unknown concentration. So C is equal to N. We've worked out what that moles was, and it tells us that we use 25 centimeters cubed, so we change it to decimeters cubed, and our unknown concentration is 0.168 mole per decimeter cubed.